as you guys are starting to solve this one, what changes are you seeing in the synthetic change?
What's an alkane to a carboxylic acid?
Not an alkane.
Or like the Y one.
Not an alkene, but the alkyne. The one with
I'm
the
like,
Y.
I can't pronounce them correctly. The triple bond.
You know, I had my my OChem 1 class the other day learning functional groups, and I had them repeat after me. Alkane, alkane, alkene, alkene, alkyne, alkyne. Because it is. It doesn't make sense, and I even remember when I was learning it, the Y I would pronounce as E sound, so it's alkene to me. Anyways, we're taking an alkyne to a carboxylic acid. That's the change that we're looking for. Have we seen that conversion before? We've seen an alkyne go to a lot of different things. We saw alkyne go to alkane, alkyne go to alkene, alkyne can go to aldehyde if it's terminal, like this one. An alkyne can go to a ketone. An alkyne can go to a halogen product, right? A tetrahalo product. Was there any reaction we saw with alkynes that took us straight to carboxylic acid? Sam's saying no. Caitlin's saying yes. Caitlin, what do you remember?
I remember what it is, and I feel like it's the O's analysis of the alkynes, where it's like the O3 and like some acid or something to get the H.
Mm-hmm. That's exactly it. Not acid though. We want a peroxide.
Yep.
And actually, the peroxide is not there to give us the H, but it's there to oxidize the carbon further. Now, ozonolysis is a cleavage reaction, and you guys can see that if we mapped our carbons, here's my aryl carbon, my benzyl carbon, and then a carbon at the end of the alkyne. Remember, benzyl is the one bonded to the benzene ring. You guys can see that I've lost a carbon in this route. I have cleaved a carbon off. So that tells me I need to do some sort of cleavage reaction. And this ozonolysis would work great. Additionally, you could use hot potassium permanganate. I think we saw that when we saw the oxidative cleavage of alkenes and alkynes. Ozonolysis and hot potassium permanganate did kind of the same effect. But there is now a new synthetic route that we could use, considering the reagents that we just learned yesterday. It actually would have to pair with some reagents we've seen in the past. This is what Sam was thinking. Take the alkyne down to an alkane. Now that I've got an alkane, I know how to do that benzylic oxidative cleavage. So there's kind of a twofold method here, or two ways to do this, two different methods that work. I know I need to do oxidative cleavage to get that carboxylic acid, and because I'm cleaving it at the benzylic position, I can either use my old method, or I can get down to a new reagent and use this new method. And again, what reagents did you choose to use?
I did the potassium permanganate.
So if anything, all we've done is added a step. But I want you guys to see that now there are a lot of different pathways. This is almost like the Marvel multiverse. You can get to the same end product by going a lot of different routes. The question is, do you want it to be a little bit of a shorter route or a little bit of a longer route? Maybe you only thought ozonolysis would work. Maybe you work in a lab where you don't have access to ozone and you don't want to figure out how to use an ozonolysis reaction. And maybe it's easier to do this other route. So feasibility in terms of applying it in a real life setting really changes based on the reagents. For instance, you guys, in a few weeks, will be synthesizing DEET, the bug spray repellent. And And we use a reagent called thionyl chloride in that reaction. You guys might remember thionyl chloride from OChem1 reactions, SOCl2. And I had a student in the spring who said, thionyl chloride in OChem1 was my favorite reagent. It's just fun to write, it's fun to look at, it's cool what it does. And then he used it in lab and was like, oh, this stuff is deadly. You don't want to get it on your skin, you don't want to inhale it, you don't want to be by its byproducts either. And he was like, suddenly I'm not such a big fan of thionyl chloride. So there's this really cool bridge between what we see in lecture and what you actually do in lab. And throughout the semester, I'll try to point that out. Okay, so we are going to wrap up our section 15 today by talking about the definition of aromaticity. So we know that aromatic rings, the benzene ring, have this term, aromaticity, kind of associated with them. You guys might see the connection, too, between aromaticity and the word aroma. That connection was built because a lot of aromatic compounds that have aromas, often contain some sort of aromatic ring. Not all. There are definitely aromatics that are not aromatic. But this aromaticity is actually an energetic stabilization. And the best way to understand the aromatic stabilization, it's the best way to look at any type of energy when talking about a molecule. It's time to go back to MO diagrams, molecular orbital theory. We're going to use something called Frost circles. Frost circles will help us predict the stability of a compound, but in addition, it makes it really easy to draw the MO diagram. So you don't have to work quite as hard as we did when we reviewed it. It's going to be a lot easier. So for benzene, what we're going to do is draw the hexagon such that it's point down. And we'll actually be able to do this with any cyclic structure. Draw the Frost circle with a point down. And now at each vertex, there's a molecular orbital. This, of course, is plotted against energy. Now you'll notice I didn't draw in the pi bonds. I don't really need to draw in the pi bonds because the Frost circle, again, just uses the shape to help you predict how many molecular orbitals there are and at what energies they lie at. Now we know from benzene that there are 6 pi electrons. And we talked about this yesterday in terms of nomenclature, that it actually doesn't matter where those pi electrons are drawn. Those are 2 equal resonance forms of each other. And so you can abbreviate the aromatic ring with this circle inside because it says it doesn't matter how many electrons are there. There's basically a double bond between every single position. This is dangerous, though. Why is it dangerous? because it doesn't say how many electrons are there. And what good is a structural drawing if you're not communicating the electrons? So this is another assumption that we have to make, is that the circle inside of the 6-membered ring represents 6 electrons. That's an assumption we have to agree on. But then if you want to take advantage of any of those electrons, you'd have to draw the individual bonding electrons. You can't draw it as a circle and show the electrons being used. So there's some danger to using that circle, but it's so much nicer, isn't it? It's hard to draw in all of those little groups. So this is a PowerPoint that you guys have access to under section 15. I put together this MO diagram. I think there might be a typo in this, but I forget. So if I see it, I'll point it out to you. Oh yeah, typo's here, but it's pretty small. It's not something you have to pay attention to. Now with all MO diagrams, what we want to do is fill in the electrons and see how those electrons predict behavior. So we have 6 pi electrons. Here we're only looking at pi orbitals. We're not looking at any of the sigma bonding. All of these MOs, they're pi orbitals. We could even label them pi 1, pi 2, pi 3, pi 4, pi 5, pi 6. Notice how there are 6 pi orbitals and there are 6 carbons that make up the aromatic ring. One molecular orbital, for each carbon atom contributing to the system. 6 pi electrons, I'm going to fill them from lowest energy to highest energy. I'll fill this bottom, most stable electron orbital first, and then half fill the 2 degenerate orbitals, equal energy orbitals, and then fully fill those orbitals. And now I've used up all 6 of my pi electrons. What we see on this diagram is that the lowest energy molecular orbital has a p orbital. Its character looks like a p orbital on each carbon atom that is completely in phase. So actually, these 2 pi electrons do look a lot like this. These 2 pi electrons are not found between any 2 of those carbons. These 2 pi electrons are found at all positions, at all times, in the same phase. That's why they're so stable. They're delocalized across the entire system. Then we look at the next highest orbital. Notice this dotted line represents a node, a region where the orbitals go from in phase to out of phase. So here the orbitals are all in phase, here the orbitals are all in phase, but together those orbitals are out of phase across the node. And that's the typo that I have here. These orbitals are in phase, these orbitals are in phase, but across the node they should be out of phase, and I don't have that. Now you'll notice something about this orbital on the right and this orbital on the left. They have the same number of nodes, but those nodes are oriented differently across the molecule, and so they change the number of lobes, or the shape of the orbital. This node cuts through a bonding region, which means that 3 atoms are in phase, 3 atoms are in phase. Whereas this node cuts through 2 of the atoms. So the electrons that occupy this orbital are never found at these 2 positions. And which 2 positions are those? It's arbitrary. Now, when we think about electron arrows, let's say we're doing a reaction, and we were to say, oh, the pi electrons from the aromatic ring go to attack something. Just like we've seen with alkene reactions, similar to alkyne reactions, we can say that the aromatic electrons can do something. Well, which electrons are those? They're definitely not the lowest energy orbitals. Lowest energy orbitals are never the first to do something. that means that it's coming from one of these two equal energy orbitals. And it's probably not the orbital on the left, because if those two electrons left, it would kind of impact 3 atoms. But on the right, this kind of resembles an alkene and alkene. So it's likely that we can predict some of the chemical changes, the electron reactivity, is happening from an orbital like this. It's a bit complicated, right? And ultimately, you don't have to understand it in depth. What I'm just trying to point out is we can see that the character of the aromatic ring does not resemble an alkene. It is incredibly unique. And then, of course, electrons can also be sent to the aromatic ring, which is going to break one of those pi bonds. And when electrons are given to a system, they have to go into an anti-bonding orbital, something that is above the median line, this average energy of 0. And you can see that the two that are of equal energy, they have the same number of nodes, but those nodes are oriented differently across the molecule. And then there's a good chance that if you break a pi bond, or if it looks like you're breaking a pi bond, you're probably putting orbitals, electrons into an orbital like this, because this resembles the most of our pi antibonding orbital. Anyways, so we've got this idea that our MO diagram tells us that this cyclic structure with these 6 pi electrons is actually more stable than if you had a linear structure conjugated with 6 pi electrons. You take hexatriene and compare it against cyclohexatriene. There is a difference in energy. The cyclization of these pi bonds, being cyclic, creates this unique MO diagram, and this unique MO diagram provides the stability. So there was a man who kind of figured all of this out, and it actually wasn't Frost. It was a man named Huckel. I think I'm forgetting an umlaut in there, but I can't remember if it's over the E or over the U. You guys know what an umlaut is? Good, so I'm not wrong about that.
Usually on the goose, but
It is normally over the U, although I have a friend whose name is Zoe. Oh, you know what? I spelled it wrong. There's no E. So that's my apologies. R.I.P. Huckel. It might be pronounced Huckel, too. Like the Buchner funnel is Buch. This might be Huckel. I have a friend whose name is Zoe, and she's got the umlaut over her E's. We call her Zoe. But her mom is, it's Zoe. So fun. So Huckel determined this rule, a trend that you could use to identify whether a compound has this energetic stabilization without having to show its MO diagram and prove it. And his rule has 3 parts. An aromatic compound must have, no, sorry, I'm going to move it over here, is cyclic. That's the first and most important thing. A compound that is acyclic or linear is not aromatic. It must be planar. We know that not all cyclic compounds are planars. Cyclohexene likes to take on a boat conformation. Cyclooctane, or even cyclooctatetraene, 4 alkenes in an 8-member ring, we'll find that that is cyclic and bends out of plane as well. And then the last rule is that it must be fully conjugated. Now, how can we look for something being fully conjugated? We talked about conjugation, right? So we're reviewing it at this point.
Bond, single bond on one, so on, and then
Do you know what? It's not a bad idea to say, look for a single bond, double bond, single bond, double bond, because that often means you've got an uninterrupted series of p orbitals. But we're going to find some molecules that don't go single bond, double bond, single bond, double bond. So we'll look for an uninterrupted series of p orbitals. Well, that basically just means that every atom is either sp2 or sp hybridized. No atom in this cyclic planar structure is allowed to be sp3. If there is any sp3 atom, it is not fully conjugated. And that's actually going to be meaningful to us because we're going to look at some aromatic compounds that we'd find some of those atoms and say, based on all of our rules that we've learned through the past, that should be sp3, and yet it's aromatic. So we'll be able to kind of reverse this and say, based on the fact that it is aromatic, we know something new about its hybridization. Huckel's rule also has a last part, which is that the number of pi electrons must be equal to, it must solve this equation, 4n plus 2, where n is a whole number integer. Is that redundant, whole number integer? I always forget. I think it's redundant. That means n can be 0, n can be 1, n can be 2, n can be 3. And if the number of pi electrons solve this equation with any number n, then that compound is aromatic. Now let's take a look at some of the structures then that can form and the number of pi electrons that fit this. So first, let's say n equals 0, then the pi electrons, a compound that has just 2 pi electrons, is aromatic. How do you get a cyclic planar structure that has only 2 pi electrons and every atom is conjugated? If you had something like a 6-membered ring, you'd have to remove 2 of these sets of electrons, which is going to create a +4 charge in the molecule. And I don't think that you'll get such a benefit from the aromatic stabilization as you would get destabilization from a +4 charge. So instead, what we see is the smallest aromatic ring possible. The cyclopropenyl cation. 3-membered ring with an alkene and a positive charge. Cyclopropenyl cation. Is it cyclic? Yes. Is it planar? Yeah, it's actually so small, it's almost impossible for this thing to bend out of plane. Is it fully conjugated? Well, this is sp2 and sp2 for sure, because they are bonded in an alkene. And carbocations are sp2 as well, because those are bonded. Sorry, losing my words a little bit. sp2 carbocations, they only have 3 electron regions, so they've got an empty p orbital. So everything is sp2. That means there's an uninterrupted series of p orbitals. This is aromatic. And if we looked at its MO diagram, based on the Frost circle, we're going to draw the point down. And now what we see are 3 molecular orbitals, one that is bonding, one that is low in energy, and 2 that are anti-bonding. And when I fill in the electrons here, they fill the lowest energy, and they stabilize the compound. So this structure is aromatic. when n equals 1, the number of pi electrons that are possible? 4n plus 2. So 4 plus 2, 6 pi electrons. Now there are actually a number of different sized rings that can take on 6 pi electrons. So we're going to look through those quick. The first one, we're going to skip over the 4-membered ring. We're going to take a 5-membered ring and put a lone pair with a negative charge on it. This is the cyclopentadienyl anion. 5-membered ring, 2 alkenes, negative charge. 6 pi electrons. Now this is where you might look at me and say, John, I have learned through Gen Chem that if I count my electron regions around an atom, then I can count up to its hybridization. And if I look at this carbon atom, it's got 3 bonding regions and a lone pair. That's 4 electron regions, s, p, p, p. That carbon atom, I'm predicting using my old training to be sp3. But now I'm telling you, this compound is aromatic. And that atom cannot be sp3. So now I ask you, why does an atom with 4 electron regions become sp3 hybridized? What is the benefit of hybridization? What is the goal? Why does hybridization occur? Stability. It minimizes electron repulsion. When you hybridize further, you're able to increase your bond angles. You're allowed to get your electrons further away. What this is saying is that now in the context of aromaticity, our typical hybridization rules don't apply. No longer will an atom be more stabilized by getting its electron pairs further away. It will be more stabilized by taking this lone pair and putting it into a p orbital so that it is able to be a part of this pi system. So this carbon atom up here, although it looks sp3, it is sp2. You guys okay with that? We're going to have to deviate from our old rules in this way. If an atom would have been sp3 by our old methods, but being sp2 allows it to complete aromaticity, it will preferentially be sp2. The next thing is we don't have to change our rules in any other context. We use the same rules up here to say 3 bonding regions, sp2 must be part of the hybridization that we need, must be part of the aromaticity. Let's look at the MO diagram for this. According to my frost circle, I'm going to point any point down. So I've got my pentagon point down. Sorry, I'm going to change my color, keep it consistent. This gives me 5 molecular orbitals, 1 for each carbon atom, or really 1 for each atom. And how many pi electrons do I have here? I've got 6. So I'll fill 2 in the lowest, 2 in the next highest, and then another 2. Now, in a minute, we're going to look at some another definition, something that's not aromatic but anti-aromatic. And so we're going to look at some of these same compounds again. All right, we've already seen when 6 pi electrons fit into a 6-membered ring. So now I want us to look at when 6 pi electrons fit into a 7-membered ring. I'm going to do that again in case you guys need some help drawing these 7-membered rings, because they're not easy. I like to start with a point up, and then instead of my hexagon coming straight down, These next two lines are going to come out to the side, and then they'll come back in, and then they get connected once at the bottom. The heptagon is a terribly challenging structure to draw. 6 pi electrons means pi bond, pi bond, pi bond, positive charge. So earlier we were saying, can we look for conjugation by saying alternating pi bond, double, or single bond, double bond, single bond, double bond? Kind of sounds like a beat. You could write a song to that. But now we're seeing we can't use that, right? Because here I've got double bond, single bond, single bond. Double bond, single, single. So it doesn't quite work as well as it used to. Now, Huckel's rule says that this compound, the cycloheptatrienyl cation, is aromatic according to being cyclic, planar, and fully conjugated. And for the same reason that the cyclopentenyl cation, we knew every atom was conjugated, we have the same thing here. It's a carbocation, we know it's sp2 inherently. All right, now I'm going to draw this upside down, which might be a challenge. Yep, definitely a challenge. And I'm going to have 7 molecular orbitals that form. And I'm going to fill in those 6 pi electrons. Now, for context, these charges on these rings are all in conjugation. They're all in resonance, which means we don't have to represent the structures in this way because that negative charge is not necessarily at any one of those positions. So that gives us our cyclopentenyl cation. We can do the benzene ring, but we have to put a positive charge to say that not only is a double bond delocalized, but a positive charge is delocalized as well. Notice now why it's also dangerous to use that circle. That circle is just implying fully conjugated. It really does not do a good job of telling you how many pi electrons are there. You have to kind of know for each instance. Our cyclopentadienyl anion, this circle with a negative charge, to say that all of the pi electrons are delocalized and the negative charge is delocalized. And then what would I do for my cycloheptatrienyl cation? Circle with delocalized positive charge. Because again, this highlights for us those pi electrons are everywhere at the same time, and that positive charge is everywhere at the same time.
I have a question for like the hepta one. If
Yeah.
there was just one double bond in there, because it would like still like that would be 2 pi electrons, would that still be aromatic, or does it need to be like all of the bonding orbitals?
Okay, just to be clear, I think you said if there was a double bond.
If there was just one double bond instead of 3.
Oh.
If that was,
Well, what would we replace it with? So if I took out this, if I took out those pi electrons, would you agree that that would create a positive charge on both atoms? And if I took out this pi electron, or that set of pi electrons? So this compound probably won't exist because of its electrostatic charge. Having that total of 5 plus charge is going to make it incredibly electrophilic. In theory, yes, it's aromatic because its equation obeys this rule. It is cyclic, it is planar, it's fully conjugated. It has pi electrons equal to 4n plus 2. But it probably won't exist for long anyways, because anything that has electrons will probably be drawn to it. Good question. What I mean, what's the curiosity there? Is it like, can we use that for something, or
Um,
just pushing the limits?
I think just pushing. I also think I was thinking, oh well, I was thinking there wouldn't have to be positive charges, but I
Yeah.
see now if there was hydrogens, then those would be not. It wouldn't be fully conjugated.
That's true. Yeah. So if these don't have positive charges, then that means that they are satisfied with their number of bonds, which means that they have 2 hydrogens at each position. They're sp3 hybridized and they're not fully conjugated.
I thought that conjugation is the double bond, single bond, and then the charge. So you're saying that if it's another charge afterwards, that's conjugated as well, even though there's no double bond
Well,
connected.
what I would say is, what you were taught conjugation is a trend to help you identify conjugation, but that's not a definition. I don't think the definition of conjugation is a double bond and a charge. That's a really common conjugated system. But conjugation is having p orbitals that in a molecular orbital diagram, and I don't think you learned MO theory, right, in your OChem 1, that in a molecular orbital diagram are all one orbital. That's conjugation. You remember learning about conjugated dienes? When you do the Diels-Alder reaction, where's the charge? There's no charge. But it's still considered conjugated because it's an uninterrupted series of p orbitals. Does that make sense? And then I think I missed the second half of your question. Oh, because were you talking about this where we had all those extra charges?
Right.
Yeah,
So,
you could have as many charges as you want.
What I'm saying, it would follow the whole positive charge.
Well, you know, kind of like here where I just say every atom is in a double bond, thus the circle, but every atom also holds that positive charge, thus the positive. If I were to take out those other 4 pi electrons, then I'd have to change it to say this. Just a circle with +5. And then I would have to do some heavy thinking to figure out the circle represents 2 pi electrons. Does that answer your question? We could represent that conjugated system this way. It just probably would explode as soon as anything that has electrons touches it, which is like everything, except for vacuum. Okay. So what happens to a system that has a different number of electrons? We looked at this what am I trying to say? Right, this 5-membered ring with a negative charge and 6 pi electrons. But what if it didn't have 6? What if it only had 4? Well, first of all, now it no longer follows Huckel's rule, right? If it has 4 pi electrons instead of 6, then that means it follows an equation 4n, not 4n plus 2. And this gives us what are called anti-aromatic compounds, or anti-aromaticity. And this occurs when a compound, 1 is planar, 2 is cyclic, 3 is fully conjugated. What? So aromatic compounds and anti-aromatic compounds are all the same. The only thing that they differ in is that the number of pi electrons is equal to 4n rather than 4n plus 2. Now you might be able to kind of infer aromaticity is this energetic stabilization. Anti-aromaticity is an energetic destabilization. But let's see why. So if n equals 0 for this equation, then the number of pi electrons is equal to what? 4. And there are 3 different ways that we'll commonly see this, or maybe not commonly, but that we could imagine to see this. Instead of the cyclopropenyl cation, let's look at the cyclopropenyl anion. 4 pi electrons. Why would this be so unstable? Look at our Frost diagram with the circles pointed down, and let's fill in those 4 pi electrons. 1, 2, 3, 4. Oh. What do you see? Unpaired electrons. You know what we call unpaired electrons? Radicals. And what are radicals? Highly reactive electron species. So why is an aromatic compound stable? Because all of its electrons are paired. Why is an anti-aromatic compound unstable? Because it has unpaired electrons in its molecular orbitals. That's going to destabilize it. You'd never guess without MO, and that's why I love MO. Let's take a look at some other ones. This is cyclobutadiene. And if we look at the Frost circle for cyclobutadiene, we're going to draw it as a diamond. 4 orbitals. What do you guys expect to find? Do you expect to find all paired electrons or unpaired? Will you find unpaired electrons? Yeah, if it's following an anti-aromatic compound or rule, then it's going to have some unpaired electrons. 1, 2, 3, 4. Cyclobutadiene is anti-aromatic because it has unpaired electrons. I think that I could have had you guys draw cyclobutadiene and you would have thought nothing about its stability. It's just a box with 2 lines, right? But now we look at the MO diagram and we can see this is not just a normal pi electron system. Let's look at our next. Let's look at the cyclopentadienyl cation. Notice how we went from anion to neutral to cation. Kind of like here, we went from anion to benzene neutral to cation. And we look at the MO diagram. What do you expect to find? Radical electrons. And I think you guys can see that if we kept going, if we went up to n equals 1, oh, I'm sorry. I made kind of a dumb error right up there at the front.
So is n equal 1?
Yeah.
Okay.
Yeah, thank you. I'm not a mathematician.
I was like, I meant 0, but yeah.
If n equals 0, then there's 0 pi electrons, and I don't know that we have a pi system like that. So I think the smallest answer here is n equals 1, where you've got 4 pi electrons. Thank you. If we expanded this and we went to n equals 2, then we could look at 8 pi electrons, which would give us the cycloheptatrienal anion. And there it has a lone pair, and that lone pair becomes delocalized, and then that delocalized lone pair creates radicals up here, and those radicals are unstable. But there is some interesting features of these compounds. Compounds will do anything they can to not be anti-aromatic. Maybe that means that they are highly reactive. So cyclobutadiene might rapidly go through a Diels-Alder reaction, or it might rapidly go through an alkene addition reaction. So let me say this. these compounds are destabilized due to their radicals. Let's just make sure we've got that down. And we can really only predict those radicals based on the MO diagram. Did you know that oxygen actually, if you look at the MO diagram for oxygen, it has some radical electrons, unpaired electrons, which is pretty odd. You wouldn't necessarily think it looking at the Lewis structure for oxygen. Odd things happen to avoid anti-aromaticity. Cyclobutadiene will stretch out. Now this is a bit exaggerated. That's okay. You can see that I still have a 4-membered ring and that I still have 2 pi bonds. But by stretching its pi bonds away from each other, the p orbitals that make up each pi bond are too far away to be conjugated. They don't overlap. They're interrupted by this huge distance. And if those orbitals don't overlap, then they can't be used to make a molecular orbital. And if they can't be used to make a molecular orbital, then this doesn't exist. And it goes back to just being 2 alkenes, not a conjugated cyclic diene structure. And then another really interesting one is cyclooctatetraene. Tetraene. 8-membered ring, 4 pi bonds. I don't know about you, but I did not draw octagons enough as a kid to have that skill down either. That takes some practice. According to Huckel's rules, would this compound be considered aromatic or anti-aromatic? Is it cyclic? Yes. Is it planar? Looks like it. But also we draw cyclohexane to look like it's planar, and we know that cyclohexane is not planar. Is it fully conjugated? Yeah, there is an uninterrupted series of p orbitals. Every atom is sp2. And then how does it obey the pi electrons? Which equation does it obey? 4n rather than 4n plus 2. It's got 8 electrons rather than 2, 6, or 10. So cyclooctatetraene would be considered anti-aromatic. But when we look at its true structure, it creates kind of this bowl shape. And, you know, it is, here's what I'm going to do to try and draw it again. I'm going to draw the front half of the bowl, and then it kind of bends behind. And those double bonds end up here, 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 and here. And what that means is that the p orbital on this atom, which is oriented in the plane of the pi bond, can no longer conjugate with the p orbital on this atom. Instead of being side to side and overlapping, those electron regions are now at an angle. They can't conjugate. And if it's no longer conjugated, then it can no longer make a molecular orbital, and those electrons will not be unpaired. Those electrons will stay in pairs. They won't be radicals. It won't be destabilized. So when it comes to asking questions on aromaticity, there really aren't a lot of anti-aromatic compounds. If you can synthesize an anti-aromatic compound, that's good. But it's probably going to be very reactive. It's going to be hard to keep it stable for long. And some compounds that you might think would be anti-aromatic will do these fun things to get out of plane. So I don't have a lot of questions on my exams or on the unit test that have anti-aromatic compounds. They're highly reactive, and they do fun stuff to get out of it. And what I've seen other instructors do and what I've seen textbooks do is they'll give problems like these two very real compounds, and they will say, assume that the molecule is planar. Which is like, okay, assume cyclohexane is planar. Why would you? We know that cyclohexane takes that boat conformation. That's its energetic form. That's the form of cyclooctatetraene. Why would you assume that it's planar? Just to show that you understand how to apply the rules. That's it. That would be the only reason to assume something is planar. I think that we can get away with not having to assume those things. So a lot of my questions don't include assume the compound is cyclic, planar, and conjugated. But sometimes you might see that. Answer the question on aromaticity assuming this. Caesar.
So you showed us two examples, but can we assume that all anti-aromatic compounds are going to try to get out of it?
They will try to get out of it, but that usually means that they will go through some sort of reaction.
No anti-aromatic. That's what I'm trying to say. This applies to every single anti-aromatic compound.
No, some anti-aromatic compounds can't get out of it. And actually, one of the best examples is the cyclopentadienyl cation. This compound is planar. It won't twist because every atom is sp2. But then there's some oddities. If you took the cycloheptatrienyl anion, if you slapped a lone pair on there, then that assumption that we used to be making about, oh, this atom, looks like it would be sp3, but if it's sp2, then it can contribute to aromaticity, but if it's sp2, then it contributes to anti-aromaticity. So we say atoms will take on higher hybridizations to stabilize electron repulsion, and some atoms take on lower hybridization to become a part of aromaticity. But if this atom takes on a lower hybridization to be a part of aromaticity, then it decreases the energy again, it destabilizes the energy again. So if it can form, it might not take in a hybridization that would make it anti-aromatic. It might try to avoid being anti-aromatic.
So like, for example, the penta original, the one I love, you would try to gain electrons or somehow to become aromatic.
It would readily take electrons. Well, to be fair, it might not even necessarily want to become aromatic. It just wants to stop being anti-aromatic. And that actually gets us to our last descriptor. So we had aromatic, anti-aromatic, and then we also have non-aromatic. And those non-aromatic compounds break any of the three rules. They stop being cyclic, they stop being planar, they stop being fully conjugated. Oh, I didn't realize when I did my anti-aromaticity, I switched cyclic and planar. I didn't mean to do that. I mean, it's not a priority list. It's not like it has to be cyclic more than it is planar. but I just like to keep it in the same order. So I want to give you guys a couple of examples of non-aromatic compounds. Here's hexatriene, kind of equivalent to the linear form of benzene. It is planar and fully conjugated, but it is not cyclic. So it's not anti-aromatic, it's not energetically destabilized, it's just non-aromatic. Here is the cyclopentadiene compound. If you guys took OChem 1 lab, we used that reagent in a Diels-Alder reaction at the end of the semester. Why is this non-aromatic? Because I've got two other cyclopentadienyl structures up here. It's not fully conjugated. And this is the tricky thing about bond line structure. You don't see those two assumed hydrogens. But that atom being sp3 breaks conjugation, does not allow for aromaticity. And then I want to show you guys a structure motif that will come up quite a bit in our next unit. I'm putting E here to signify electrophile, something that the aromatic ring can take its electrons and bond to. Why is this not aromatic or anti-aromatic? How many, is it cyclic? Yeah. Is it planar? Probably. Most of those atoms would be planar. Is it fully conjugated? No. That's an sp3 atom right there. That atom is explicitly bonded to 4 different things. It has to take on sp3 hybridization. It's a little bit different than the lone pair. A lone pair can be placed into an unhybridized p orbital and go into aromaticity. But a bond can't. And what's even more confusing is that we won't always see this as a drawing with both the hydrogen and the additional group, which is the tricky part about bond line structure, where we assume that this hydrogen is here. We have to show all of the charges, and there's no charge on that atom. That means that atom has a full valence set. It's got 8 electrons. It's got 4 bonds. Where is the 4th bond? It's the bond to the hydrogen that's assumed. Still non-aromatic. You have a question?
It might be if let's say there was a positive charge by the E or whatever that group is, would it then? Well,
So if the compound took on a total 2+ charge,
yeah. I guess.
then it would be anti-aromatic.
Oh, yes.
So it would be stable. It would be very unstable for 2 reasons: very high electrostatic charge and very low stability. It'd have the anti-aromatic destabilization. But we won't see it. That is a common motif, a bonding pattern that we'll see in the next section when we do reactions. Which means aromatic rings can break their aromaticity, but then they love to do things that bring their aromaticity back, because that's going to provide stability again for them. All right, I want to give you guys a break because I know that MO theory is just the light of your lives. So let's take 5 minutes or less. Get up, move around, get your blood flowing, and we'll come back in. Keep going here.
I think we should have it. Oh, question that. Sorry.
Yeah.
I'm not sure. I don't understand. What is I know he's gonna no N. I know it's a dumb
Oh, n is a whole number integer.
question. Yeah, but I don't understand why it goes to 1 and 2. I don't know what's that. But that's what we
N
so in this
is a
case-
variable,
Right.
which means it can change.
Here's 0. If you go 2 and 0, then that's 0. Plus 2.
No.
Okay, that's 2. Okay.
Wait, let me grab my marker. And we'll
Mathematically, I don't understand
we'll
why
plug it
it's
into the equation. We're looking at this equation. The number of pi electrons being equal to this equation.
Oh, okay.
So when n equals 0, the number of
That
pi electrons equals 4 times 0 plus 2 equals 2. Or when n equals 1, the number of pi electrons equals 4 times 1 plus 2, 6. So we're just looking at solutions to the equation.
But
And,
it's just
and then in the context of those molecules.
it's just the integer means 0, 1, 2, 3.
Yep.
It's not an actual variable. Like not variable.
It's not a part of the molecule
Part
at
of
all.
the
That's right. It has nothing to do with the molecule other than it solves the equation for that molecule's pi electrons.
Could there be another compound with the same number of electrons in? That is not right. So that
Yeah.
also would have. They could be.
Yeah. There are few compounds that have only 2 pi electrons. There are many compounds that have 6 pi electrons. And then there are a lot of compounds that have 10 and more. You
But-
look at those big polycyclic structures.
But at those definitions, your minimum for each one of them would be 2 and 4. You could have an anti-aromatic with less than.
That's true. Yep, exactly. Minimum to be aromatic is 2. Minimum to be anti-aromatic is 4. Maximum is theoretically infinite. Yeah. Good question.
I don't know.
No, I get it. In fact, I get that a lot. And I think it's because very little of what we ever do in organic chemistry has nothing to do with the molecule, right? And the integer here, it has nothing to do with the molecule. It's just a way of solving the equation. Do you guys know what term we give to this lone pair of electrons in the cyclopentadienyl anion?
Oops.
What terminology can we use to describe those pi electrons? They can be nucleophilic. Yep. You know, there's a really cool thing, cyclopentadienyl anion. Because it has that MO orbital, that molecular orbital that is all in phase, it can actually overlap with iron. And iron has a D orbital that looks like this. And then this ring can sit on top of it with all of its p orbitals facing down, and they can interact with the d orbital. It's very cool. This creates an organometallic complex where the entire ion bonds to the iron. And then it actually does the same thing on the bottom side as well. And we call it ferrocene, but it was the first reported sandwich structure, where a metal atom was sandwiched between 2 organic molecules. That is beyond the depth of this course, but it's a pretty interesting idea. What terminology do we use to describe this lone pair? We'll use either localized or delocalized. And because it is involved in aromaticity, it is not found at any one atom in particular. It is delocalized through the structure. That's what we'll say. Now, I want to use that as we move into the next kind of class of compounds. There's two classes. I think that what I want to look at first are the polycyclic aromatics. You guys will notice when I word questions about these compounds, I often ask, rather than saying, is the compound aromatic or anti-aromatic or non-aromatic? Oftentimes I ask, which compound has aromatic character? Or does this compound have aromatic character? So benzene, of course, we know has aromatic character. But if I take on another ring that is also basically benzene fused together. The other day we called this naphthalene. This compound is also aromatic. So I count the entire structure and all of the pi electrons in it. That's 2, 4, 6, 8, 10 pi electrons, which obeys the 4n plus 2 rule, where n equals 2. Aromatic. Has aromatic character. And then let's take a look at this type of reaction, or this type of ring we kind of used in our benzylic reactions. It's got an aromatic ring on the left and a non-aromatic ring on the right. Is this compound aromatic or non-aromatic? Oh, well, there lies the trouble in the terminology. This ring is definitely aromatic on the left and non-aromatic on the right. So what we can say is that this compound has aromatic character. Does that seem fair? The entire structure is not aromatic. Not every carbon in the molecule is aromatic, but the molecule has aromatic character. And in fact, this can even apply to a structure that is conjugated with my aromatic ring. So here's kind of an in-between. It has one pi bond that is in an uninterrupted series to the aromatic ring, but the ring on the right is not fully conjugated. I've got these two sp2 hybridized atoms. So the ring on the left is still aromatic. It has pi electrons equal to 6. I don't count the pi electrons that are not in the ring that is aromatic. Those pi electrons are a part of the non-aromatic side, but we say the same thing. This compound has aromatic character. It also has an alkene. It also has alkane, but it has aromatic character. Let's go back to a bicyclic structure that breaks aromaticity. You'll notice that the ring on the left looks like benzene. The ring on the right looks like the cyclopentadienyl cation. And the cation we saw was anti-aromatic, but benzene we know is aromatic. So is the molecule aromatic, anti-aromatic, or non-aromatic? Similar to up here, we're going to count all of the pi electrons for the whole structure, which is different than what we did here. Here we only counted those 6 pi electrons that made the left-hand ring aromatic, and we ignored the 2 pi electrons that were not within the aromatic portion. It feels like we're kind of picking and choosing when to count pi electrons, but the answer is any part of the ring that is conjugated, fully conjugated, excuse me. Any part of a bicyclic structure that is fully conjugated, you have to count all of those pi electrons. And in this structure, everything is fully conjugated. So we have to count all of those pi electrons. Pi electrons equal 2, 4, 6, 8. 8 pi electrons obeys 4n. This compound as a whole is anti-aromatic. Does that feel odd at all? Because it looks like it's got a benzene portion. But the benzene portion is fully conjugated with the other portion. So the other portion is basically robbing benzene of its aromatic character. Now we're not going to look at frost circles for these. They get a little bit too complicated. But what we can imagine is that by being fully conjugated, the way the electrons are spread out creates radical electrons. That's going to destabilize it. So the rule, if all rings are fully conjugated, count all pi electrons. And if any ring is not fully conjugated, count none of its pi electrons. Like we had this ring on the right that was not fully conjugated, so I didn't count its 2 pi electrons. You guys okay with this? This is just an easy rule to take a polycyclic and look at it and say, is it aromatic or not? Or anti-aromatic. We've only been considering carbon rings, but what if there's a heteroatom in that cyclic structure? So here's a compound called furane. You guys may have heard of the solvent tetrahydrofurane, where I add 4 carbons across the 2 pi bonds. THF is a very common ether solvent. It's a derivative of furane. Furane is an aromatic compound. In order to be aromatic, every atom must be fully conjugated, including the oxygen. So what hybridization must oxygen have to be considered fully conjugated? It cannot be sp3. And it would either need to be sp or sp2. More likely in this case, sp2. But this is a bonding environment where we would predict oxygen is sp3. 2 lone pairs, 2 bonding pairs, 4 electron regions, sp3. So I can tell you this compound is aromatic, and then we have to decide the oxygen is not sp3 hybridized. It's actually sp2 hybridized, and one of its lone pairs sit in a p orbital. But by being in a p orbital, it's not isolated to oxygen. It's in a p orbital that is conjugated with the rest of the structure. And that's going to get us to this idea of localized lone pairs of electrons and delocalized lone pairs of electrons on our heteroatoms. In our notes, let's start with this compound. This is pyridine. Pyridine is often abbreviated as PY or maybe PYR. And you can see that pyridine resembles what compound? Definitely looks like benzene. Just take out one of those carbons and its hydrogen and replace it with a nitrogen and a lone pair. Now, is it any question what hybridization nitrogen is? It shouldn't be. It's in a pi bond. This atom has 3 electron regions, a lone pair, a single bond, and a double bond. And because it has a double bond, it must have a p orbital, which means it cannot be sp3 hybridized. It must be sp2. So this structure is cyclic, planar, fully conjugated. But what about the number of pi electrons? Certainly this structure has 2, 4, 6 pi electrons. But what about this pair right here? Is that pair in the p orbital engaged in aromaticity? Or is that lone pair in a hybridized orbital, perpendicular to the plane of aromaticity? What tells you that?
Because if not, it would be anti-aromatic.
Okay, so you've got a good point. If I count this lone pair, it would be an anti-aromatic compound. And pyridine is a very common compound, which means it's probably not anti-aromatic. So we can use just common sense to say it's probably in a hybridized orbital, and it's not involved in aromaticity. But we can also use another way to say this. We can look at this another way, which is nitrogen has 3 sp2 orbitals and a p orbital. How is it going to use those? One of the sp2 orbitals goes to its single bond on the left. One of its sp2 orbitals and its p orbital goes to the double bond on the right. Do you guys agree? Every bond between 2 atoms has to have a sigma bond. And those sigma bonds come from hybridized orbitals. And every double bond has to come from a p orbital. So nitrogen, by being explicitly shown in a pi bond, has a p orbital that is already occupied. What does that leave for the lone pair? It leaves this sp2 orbital. This is the lone pair. And that lone pair, by not being in a p orbital, is not involved in aromaticity. That lone pair is localized to nitrogen. Nitrogen holds that lone pair. No other atom gets to share that lone pair. So we could actually abbreviate pyridine in this cyclic form, right? We don't have to draw the double bonds. We could draw it with that circle, and guess what we would still show? The lone pair, because it's localized to nitrogen. Now, I want you guys to recognize really common bonding patterns. So when you see this nitrogen with a double bond and single bond and a lone pair, I'm going to refer to that as a pyridynyl lone pair, because that's exactly how nitrogen and pyridine shows up. And pyridynyl lone pairs are localized lone pairs. They do not engage in aromaticity. No aromaticity. Is that okay? It's not a pi electron. But we know that this is not the only way that nitrogen shows up in a molecule. So I want to look at this structure next. This structure is called imidazole. I did a lot of undergraduate research with imidazole and methylimidazole. You'll notice that imidazole is in a different bonding environment than pyridine, but it still has this lone pair. And at first approach, we look at nitrogen and say 3 bonding regions, 1 lone pair region, 4 total regions, SPPP, sp3 hybridized. Okay, if nitrogen is sp3 hybridized, then how is the compound labeled? Non-aromatic. And nitrogen would take on an sp3 hybridization in order to minimize electron repulsion. But if nitrogen was sp2 hybridized, then the lone pair must go into a p orbital. There would still be 3 sp2 orbitals, but that would be sp2, sp2, sp2. All of its bonding regions would be sp2, and its non-bonding region, its lone pair, would be in the p orbital. So let's say that. If sp2, then the lone pair is in p orbital, and if the lone pair is in the p orbital, every atom is conjugated, and the pi electron count is 2, 4, 6. What would that make the compound? Aromatic. So what will the nitrogen prefer? What is the best option energetically?
Aromatic.
Become aromatic, take on an sp2 hybridization. So now I want us to recognize the pyridynyl bonding pattern. And I want you to recognize the imidazolian, I'm making up that word. The imidazolian lone pair. It looks good, right? Oh, I missed my Z though, didn't I? I kind of skipped it. Imidazolian. So that is a lone pair that we would have anticipated to be sp3, but allows the molecule to become aromatic. Imidazolian lone pair are delocalized. And what does that mean? Yes, they're in a p orbital. They're engaged in aromaticity. They're taking part in the aromatic compound. They count towards the aromatic pi electrons. Now let's take this back to furane. We noticed that furane had oxygen instead of nitrogen. And you can see that by taking on an sp2 hybridization, one of oxygen's lone pairs is delocalized, one of oxygen's lone pairs is localized. And we can do kind of the same thought process. This is for fluorine. If this oxygen is sp3 as we suspect, then the compound is non-aromatic. But if this compound is sp2, one lone pair is localized, one lone pair is delocalized. One of them is in an sp2 orbital, one of them is in a p orbital. So how many do you count towards aromaticity? Both? Just the one. Which one? Well, you're right. You look at the structure, it doesn't matter which one. But the delocalized one counts towards aromaticity. The localized lone pair does not count towards aromaticity. So how many pi electrons in imidazole? 2, 4 from the obvious pi bonds, and I said imidazole, sorry, in fluorine, and one of the lone pairs from the oxygen. So this is going to be a common question on your homework, your unit tests, your exams. What is the hybridization of nitrogen or oxygen in these atoms? And also, what is the pi electron count? So you need to be able to count the electrons that are meaningful and avoid the electrons that are localized. Count the delocalized, don't count the localized. How do you know that if you don't know the hybridization of them? There is another type of bonding pattern that oxygen takes on. I don't have a good example name for it, so I think we could look at these anthocyanins. These are pigment molecules that are pretty common. I don't want to look at the whole thing though. I'm going to shorthand this to just a 6-membered ring. You'll notice that this puts a positive charge on oxygen, which means instead of having 2 lone pairs, the oxygen now just has 1 lone pair. Does the lone pair count towards aromaticity or not? Which of these other cases does this 3-bonded oxygen resemble most? It resembles pyridine the most. So we could actually say that this lone pair is a pyridinyl lone pair, which means that it is localized or delocalized. This is a localized lone pair, not in the aromatic system. Woo, I barely got through that. I apologize for always taking you guys like so close to the end of the hour, just beating this information into you. Now, go practice. Go do the homeworks. Start reviewing the midterm. We are less than a month away now, just under, about a month away from our midterm exam. And if you are struggling to apply these problems or these concepts, if you feel like the homework is not making sense or even like feeling too easy, go look at the midterm and the final and look for these types of problems and see if you can answer them. That would be a good way to apply your learning to these. Okay. Oh, it's Thursday. I was so looking forward to seeing you guys tomorrow. We're done with section 15. We've covered everything we need to in terms of aromaticity. So now on Tuesday when we come in, we're going to be looking at reactions with aromatic compounds. Two major classes. Aromatics acting as nucleophiles and aromatics acting as electrophiles. We're also going to start doing mechanisms and electron arrow pushings. So there's a few things that I will try to go through quickly when it comes to section 16, and a few things that I want to really spend some time on so that we get it nailed down. So do your section 16 pre-reading over the weekend if you haven't already. Get a feel for what we're going to look at. Get some question marks in your brain. We'll come back in on Tuesday and we'll answer them, okay? Have a good weekend, guys.